Thank you very much, Professor Panda, for the invitation and the opportunity to talk, and Hari for making all the arrangements. I am going to talk today a bit about applications, but I'm hopefully in the course of the next 25-30 minutes also give you a different perspective on MPI and MBAPH. This is work done with students and senior research programmers in my group, and although this is work I'll try to show you is building up a lot on work that's happening in the national labs, the bulk of this work is pretty much done at the Radical group at Rutgers University. So here's a very high-level organization for the next 25 minutes. I want to take a few minutes, 5 minutes, to try to motivate what I call the many-task approach. Some people will call these workflows, some people will call these many-task workloads. We won't get into naming issues. I'll try to get across the motivation and try to explain to you why this perspective of many tasks, where each task is an MPI task in of itself, is going to become increasingly important. And as they become more important, I want to point out that there are many reasons why the challenges, both that this application perspective provides, is a different challenge to the ones that we've historically and traditionally considered. So on the one hand, workflows, application workflows aren't what they used to be. And on the other hand, some of our historical system software and middleware isn't ready to support these requirements. And I'm going to try to talk about what I argue is maybe one of the few innovations in workflow systems in the past 2 decades or so. The concept of workflow systems have been around for long, but I argue, and I even contend with an intention to provoke, that there's been very little, if any, innovation in workflow systems for well over 2 decades. And what this mandates, this changing landscape, what this mandates is a fresh perspective to workflow systems. And to be precise, I'll be talking about the middleware upon which workflow systems are built. But very quickly, this will lead to discussing what I call the pilot abstraction, and this is where the connection with MPI comes in, and a specific implementation of the pilot abstraction. That particular implementation is called Radical Pilot, no points for guessing why, but it's a very complex landscape to understand the full performance consideration. So I'm going to try to tease out just one dimension of this many-dimensional aspect of performance, as performance typically is, and with the hope that there'll be some discussion either immediately after this talk or with others from the MBAPH team as to how we might start thinking about performance considerations. So as I said, this is going to be, in the first few minutes, I'm going to take a perspective of a lot of applications, and even there, whereas ultimately the applicability of these ideas is going to be very broad. It's going to be everything from seismic physics on the one hand to data-intensive applications on the other hand. Exposing some of my own biases working with the biomolecular science community, I'm going to for a while just draw your attention into biomolecular sciences, and in particular molecular dynamics. Now, there's no loss of generality here. That's the first thing I want to assure you. And the second thing I want to assure you is that this is a darn important problem. 33% approximately of all supercomputing cycles on NSF infrastructures, resources, are consumed by biomolecular sciences for MD. Now, sometimes it's materials, sometimes it's biophysical systems, whole range. So without loss of generality, let's talk about biomolecular simulations, which allows me to make some specific suggestions, claims. So we heard in Amit's very nice talk this morning about these large systems. People like Klaus Schulten and others have studied million atom, 10 million atom plus HIV capsids, fully atomistic, very large, running on tens of thousands of nodes and cores. That's a very important type of, if you will, molecular dynamic simulation. And in many ways, these very large biomolecular systems require the ability to weak scale. But there's another very important dimension in biomolecular simulations, namely the ability to reach adequate timescales. It's not enough to just run a simulation of a large system, but for a very short duration. But the end of Dennard scaling and other trends has made the ability to get to long time scales increasingly hard. Now, if you were D. Shaw and you had a few extra $1 billion in your back pocket, you'd create a new computer called Anton and get to long time scales, in this case 800 microseconds approaching a millisecond, and then start seeing phenomena of very significant interest, but at very long time scales. But for those of us without a few extra $1 billion to spare, innovation is what, the algorithmic innovation is what is needed. And the community has moved away, the biomolecular simulations community has moved away from running these single long simulations of a single MPI to try to get the same physics, to get the same insight, but now running many smaller duration, but running many such simulations, i.e. running many ensembles of a molecular dynamics simulation. Now this is one important trend, and people like Cheatham and others who will know, and a whole bunch of my colleagues are kind of, the jury is still out as to which is the best way to get the right science. Single long simulations, one long trajectory, or many smaller ensembles of independent trajectories. Now, we won't get into the details of this. This is still a very involved question and arguably more domain specific, but the point I'm trying to convey, first point, is there is a trend towards running large ensembles of molecular dynamic simulations, each one of these being a full-fledged MPI job in of itself. Lest you think we're in the era and we're just talking about trivial bags of tasks, I want to quickly move your attention towards another important addition. We're not just talking about embarrassingly parallel bags of tasks. We are talking about independent MD simulations which will, once in a while, interact with each other. I repeat, which will, once in a while, interact with each other. And again, there's a whole class of algorithms which I won't get into, but we'll just call them ensemble-based adaptive algorithms, where intermediate data is used to determine the next steps. And if nothing else, there's literature that shows that when you take these kinds of approaches, you get factors of 1,000 and even more improvements over both the multiple non-interacting trajectories as well as the single long trajectory. So that's your overview to biomolecular simulations in a nutshell. And just to try to give you some quick examples of these interacting ensembles, there are classes of applications called replica exchange, where you have a large number of replicas interchangeably used with ensembles. They run, but then they exchange some trivial state temperature, some other order parameter, or they could be more complex global reduction style operations. Or here, again, pardon the resolution, I realize is not very good, where the number of simulations that is being added or removed changes from stage to stage. So you might start off with 100 ensemble members, but you realize that, look, there's something not good happening, I'm missing some value, so I might add new. So you might go from 100 MPI simulations to 110, the 10 being at particularly carefully chosen parameters. So long story short, you get the idea that there are a large class of algorithms, adaptive algorithms, which involve the interaction of these individual MD simulations. Again, one last point here, important to make, is that for a whole set of reasons, you want to keep the adaptive logic outside of the MD code. These MD codes, once again, like Amit referred to, GROMACS, NAMD, AMBER, highly optimized, very efficient, and you don't want, as an end user, to go in and be modifying them. You want to have the interaction of these outside of the MD code, so you treat the MD code as a black box, and this is where a lot of the domain-specific algorithmic innovation lies, to try to think of what are the different algorithms, adaptive algorithms, that will allow you to do your science better without getting into the highly non-trivial enterprise of modifying MD kernels. Okay, so the adaptive logic is separate, and you'll see why this is important coming back later. Okay. So this is trying to focus your attention on biomolecular simulations. Before I get into any details, I just want to, at the risk of repetition, remind you that what I told you is true for biomolecular sciences, but is true for a large, broad swath of different domains. Climate sciences, which I work with, high energy physics, a different set of considerations, climate sciences, and seismic physics, beg your pardon, and some of the same questions arise. So as I said, one needs to take a fresh perspective to workflows. Why? Now, if you look at the history of cyber infrastructure, you'll realize that workflows came into being very much in the era when some of your big science projects were coming around. People started thinking about how am I going to support the data analysis requirements of the LHC? How am I going to support the data analysis requirements of LIGO? Big science projects. And there have been important consequences the important technical consequences of that. Namely, that in these big science projects, you had obviously thousands of domain scientists, and you had a bunch of computer scientists, cyber infrastructure specialists, devoted to supporting the needs of those big science projects. So in some ways, you had dedicated computer scientists, cyber infrastructures to get those workflows going. Statement number one. Statement number two, if you do a careful analysis, and I'll just talk about LIGO because that's one that I'm intimately familiar with, there are 50 different workflows that are part of the LIGO suite. But actually exactly one of those 50 consumes about 96% of all computational requirements, right? And so remaining 49 have not been optimized, but the one has been heavily optimized. So you've got, for the whole of LIGO, you've essentially got one important workflow which has then been carefully optimized. Not to mention that in the era of the starting of these big science projects, the software infrastructure was fragile, unreliable, missing services, so there was a need for these computer scientists. Fast forward to now, fast forward to the era where the algorithm, the examples I gave you in biomolecular sciences, the adaptive algorithms, that is a representation of both the scientific innovation, the algorithmic innovation, but also there are many different domain scientists coming up with their own algorithms, their own workflows, which they need to run at scale. So importantly, now you not only have one or two kind of well-defined workflows that you can optimize the hell out of, but you've got many different workflows, and increasingly that the developer of the workflow is also often the domain scientist. This is the important change. So all the algorithms that I gave you are not developed by computer scientists and engineers like myself, but they're coming from the domain scientists, my collaborators who are card-carrying biomolecular simulations people, and they want to test their algorithms at scale. So workflows are not do it once and then run it for the next 20 years. This is the very manifestation of the innovation of these domain scientists. And that's why you need a fresh perspective. You no longer just want to worry about the end users of the workflows, but you've just now conflated the end user and the developer as being possibly the same person, right? And so that's why you now need to change your perspective on saying, here's a workflow system, wonderful to use, to start thinking about how are you going to support the very development of these workflows and workflow systems to support that. And with this set of arguments in mind, I ask that we move away from this workflow system vendor lock-in mode to asking what are the right components using which appropriate workflow systems and thereby workflows can be developed. And no surprises, when you think of this diversity of workflows, the distinction, the last mile, if you will, customization, you'll understand that there's really no easy way to answer this question. And in some ways, the proliferation of many workflow systems, hundreds, and if you follow the open common workflow language, a listing of 250 plus and growing workflow systems, you'll understand that this is a very true matter of fact, and people have responded by rolling up their own workflow system. So on the one hand, you have these fixed workflow systems, somewhat rigid, somewhat difficult to extend on your own. But at the other hand, you have this proliferation, potpourri of 250 workflow systems. Clearly, neither is appropriate. So what's the appropriate software engineering approach to try to prevent the proliferation on the one hand, yet not have this vendor lock-in rigidity of the other? Okay? And that is where we talk about building blocks approach to workflow systems. And thinking about this, I need to get a bit more specific, and I try to say there are many different ways to think about building blocks, but for the purposes of this discussion, let's say there are 4 levels. At the very high level, the applications workflows. But the 2 important ones are, if you will, the task runtime system, where a task is an MPI simulation for the purposes of this talk. And then there's the level which is managing the many tasks, deciding the mapping of the task, deciding the scheduling, which tasks should go on to where. So if you will, those of you familiar with traditional DAG representations, how do you resolve, how do you decide how to execute the DAG without worrying about how the execution is actually orchestrated on a given system. One implementation of this, if you will, stack is the CyberTools approach, and I obviously want to go straight into Radical Pilot, that is the hero of this talk, but I want to quickly talk to you so that you get a perspective of what I mean by the building block approach, is to give you a very quick example of what I would call a domain-specific workflow system. I'll talk about something called the Ensemble Toolkit, which is a component that sits above this pilot layer, and I know I have not defined the pilot layer, but which is being used to support many different workflow systems, right? So I'm going to talk to you a bit about Ensemble Toolkit. I'm going to talk to you about a high-throughput binding affinity calculator, but what I want to tell you is that this component, this building block, has been used to support many different domain-specific workflow systems, and all of these use Ensemble Toolkit. Ensemble Toolkit uses Radical Pilot, but by no means, hopefully as this diagram shows you, is it necessary to use this when using this, nor is it necessary to use this when using this. So going back to the original design objectives. Just to prove this, in some ways, there are papers where we work with the Swift team, another workflow system, that has swapped out a component and used one of these components. And that's been done with also the Atlas LHC project, where they've taken specific components from here and swapped their workflow management system. So you start understanding from a components point of view what I mean by building blocks for workflow systems. Okay, now coming back to the specifics. So this is actually something which was at CC Grid, which Professor Panda was a program chair for, a great conference. This was part of the scale challenge, and luckily actually won the scale challenge. This is to try to compute binding affinities. This is critical for effective drug design, so on and so forth. What I want you to appreciate, again, not all the details, is the highest level, that what you're able to do with these domain-specific workflows is for the specific algorithms that the domain scientist wants. Again, details I will not get into, something called ties, something called SMAX, black box algorithms. You can provide the right APIs, which then can be used to develop these very custom, very specific workflows, okay? Without having to worry about the many considerations that it takes to get the scale, to get the performance. Now, this is possible because this in turn uses a layer below, which in turn uses called Ensemble Toolkit, which then uses other layers below. So what is the Ensemble Toolkit? It's, if you will, a workload management system. It's a toolkit to manage the complexity of acquisition and task execution for ensemble-based applications. And hopefully I've told you that there are many different ensemble-based applications. So this is this one additional, if you will, abstraction that has the right programming model, something called the pipeline stage task programming model, that then can be used to develop many different ensemble-based applications, one example of which was binding affinity calculation, which in turn has its own, if you will, well-defined API, very close to the end user's requirement. Okay? So now, oh sorry, I should have just said, and whereas this has its well-defined programming model, what it really is using is the pilot layer to manage the execution of all of these ensembles. So now, 10 minutes in, I think I should try to explain what is the pilot abstraction. So in simple terms, it's a system that generalizes the placeholder job to allow application level control of acquired resources via a scheduling overlay. So let's look at the schematic. So think of all of these as your ensemble members, right? Each of which could be an MPI job, and you could have many of these. So instead of your traditional submitting an MPI job directly onto a resource, notice the level of indirection. What you submit is a pilot job, which is this empty container job, right? Which goes through your resource manager, Slurm, what have you, and lands up on, let's say, a set of nodes. And notice, again, this is essentially an empty MPI job because it has no tasks assigned to it. Right? Very simple. Now, what happens is once this is through the queue and is active, again, push, pull, these are all trivial details, inconsequential details. What happens is this then dials home, in this case through these particular system, pilot job system, and these ensemble-based MPI applications can be assigned to these tasks, to these pilot job containers, right? So the concept is something which I'm sure you're familiar with, you've thought about, done in various ways. So in of itself, a fairly simple, if not a trivial argument. And this is proven by the fact that pilot jobs have been around even before they were ever called pilot jobs. When we did a careful literature analysis, we found that the first concept that I outlined goes back to early 90s, and as I said, they weren't even called pilot jobs. But all of these, as some of you will realize, were consequences of the fact that the LHC was being built. People were starting to build the LHC infrastructure, and there was a proliferation of pilot jobs, and also, by the way, of workflow systems. But that's besides the point right now. And all of these were for your traditional distributed high-throughput computing, where each task was typically one core. I argue, and at least for the people who reviewed this paper, they believe this argument, that the first pilot job system designed specifically for MPI jobs was Radical Pilot, right? And then what we do is we talk about what is the normative architecture of all of these 20 plus different pilot jobs, and how do you generalize them to actually support MPI jobs. Again, won't get into the details, but for all the gory details are in this suite of papers. And so what I've really tried to show you is that this concept of distributed high throughput computing, when carefully generalized, can support late binding of workloads on HPC, even though this concept began very much in the distributed high throughput computing context. And that's really what I call a generalization of the scheduling overlay, which generalizes the recurring concept of using a placeholder as a container for compute tasks. And advantages, first, you see that it decouples the specification of the workload from the resource management. Contrast this with your traditional submitting an MPI task into the Slurm queue resource management straight away. Enables a fine-grained spatiotemporal control of the resources. So you get your 1,000 nodes. You decide how you want to slice and dice that. 1,000 one-node jobs or 10 100-node jobs. And you can change that over the course of your execution. And as I've pointed out, you can build higher-level frameworks and tools without exposing any of the details of the resource management to the end user. Remember, the starting motivation, right? So here's a quick executional, you've seen the schematic, but just for Radical Pilot, this is the specific execution model with the appropriate temporal stamps. Again, the core part here to think about is the agent. These four components that are in purple are the software modules. And I want to get down into talking a bit about the agent and talking a bit about the performance aspects, right? So as I said, the four purple are the four main modules, and within the agent there's the scheduler and the executor. I'm going to talk very quickly about the executor, which is the component of the agent, remember the entity that has landed, that has acquired the resources, and now that will manage the execution of the individual MPI tasks on the resources acquired. I'm going to talk a bit about the executor and then show how these two components are actually often not in tension, but you have to design carefully to get these to work in coordination to get the adequate performance. Okay, so in the interest of time, I'll skip the state model and I'll skip the programming model. I just wanted to provide a quick overview that there is a nice Pythonic interface to all of this. And remember, the whole idea is to build higher level tools, and these are therefore very important so as to be able to easily use the pilot job, radical pilot, which again is different from all the others. Okay. So at this stage, I want to talk about the executor. So why not run directly into Slurm? So substitute AP run with your favorite. And there are a whole set of reasons. And I'm getting slightly case specific here. But you can't, there's a throughput issue. How quickly can you start these jobs through a Slurm or an AP run? And there's a limitation there. Changes from machine to machine, from resource manager to resource manager. But what I'm going to try to show you is we're trying to be able to marshal approximately 10,000 MPI jobs at a given instant of time. Sometimes these MPI jobs could be as short as a few seconds each. They're typically a minute, 15 minutes, but they could be very short. And you have to get them all started through. So whether you're talking about Slurm, AP run, whatever, the throughput is very small, and often there's constraints on the granularity of the job. Sometimes, as is often the case, one task would go to one node. Obviously, sometimes tasks have to go to many nodes, but sometimes tasks might have to go to less than a node, and you might have all of these mixes of task sizes at the same instant of time. So in the interest of time, this was, as I said, for case specific, and I won't get into this. For those of you interested, this is the equivalent of the Hydra component in Mvapage and elsewhere. And what I'm trying to show you here is that it is not easy to get what I will call the flatline behavior. Namely, if you have a large number of tasks, each running for approximately a minute, and you have 3 generations. So you run, let's say, 100 of these 1-minute tasks, and then as soon as they finish, you run another 100 of them, and as soon as they finish, you run another 100. So 3 generations of 100. So you can understand that they should, in an ideal scenario, all flatline to 192 seconds. And you can see that at these small counts, you do get that behavior, but as you get to larger and larger number of nodes, the ability to use something like ALPS or Slurm to launch jobs of 64-second durations and launch hundreds of them or thousands of them becomes increasingly difficult, and that's why you see lines like with this very high gradient. Okay. Now, this is a second quick view of this. Actually, let me skip this in the interest of time and try to tell you this particular plot, because there's a lot of interesting details there. So this is now trying to say you're trying to run these tasks. In this case, they're approximately close to 880 seconds, and I'll explain why 880 seconds. That's the average size of these MD, average duration of these MD tasks. And what you're doing here is you've got a large number of tasks. So here 512, and here you've got 4,000 of these. Each of these is an MPI task over 2 nodes, right? So if you look at this, this is running over approximately 128,000 cores. This is on Titan and Blue Waters, and this one's approximately over 16,000 cores. Now, the first thing that you notice is that for 512 MPI tasks, you're about finishing more or less where you'd expect. So you're able to design the agent and be able to execute 512 2-node MPI jobs with a small gradient. But by the time you get to 4,000 of them, and you're running on 128,000 cores, you can see that the time to execute is highly non-trivial. So you're spawning about 4,000 MPI jobs, and you can see the gradient and some transition from here to here at intermediate node counts. Okay, and one other way of looking at this is, given the different number of tasks on the different number of cores, what is the overhead of execution, so of spawning an MPI job within this MPI job? Oops, sorry. And as you can see, the cost, the red is what is useful work. This and this are, if you will, wasted work. This is a direct reflection of the inefficiency of executing and spawning an MPI job within this agent. And you can see that that is slowly but steadily becoming the dominant part. This is, again, the slide I skipped, which is about the interaction of the scheduler and the agent. But you can see that both become very important considerations, and you're really just getting 30% approximately of utilization at these large core counts with large number of MPI tasks being spawned. And the many details, as I said, I just wanted to kind of motivate some discussion with the Mvapage team. And one of the many reasons why we have this, well, there are many, but one is that we have to design for generality, we have to design for heterogeneity. Namely that when you don't make any assumptions on the homogeneity of the tasks, and I've hopefully motivated why this is so important, because you're going to have tasks of very different kinds, then this is the performance, i.e. poor. But the minute you relax that and you say, by definition, all my tasks are going to be uniform, you can improve. So you can reduce that 30% overhead to quite a small amount. So just trying to, again, close out by reminding you that I've talked about biomolecular simulations, but the considerations are true for streaming systems, and again, working within the DOE context, this is very important, to seismic physics. And for those of you at ICPP next week, you'll realize that this is also very important for high-performance data-intensive systems, and these concepts have been applied to understand different types of trajectory data. So what's my last slide? Let me just conclude. So hopefully I don't need to convince you that the importance and diversity of workflows is going to increase. And I've hopefully also convinced you why there is a need for a fresh perspective, namely a building blocks approach to workflows. One particular building block, one particular component is the radical pilot component, which is an implementation of the pilot abstraction. And I've tried to show you some of the engineering challenges of managing many thousands of concurrent MPI jobs. And just for this particular instance, we're at about 10,000 MPI concurrent simulations. There's a price for heterogeneity. We've got a lot of scheduling optimization to be done. But as soon as we overcome the scheduling optimization, there are many, many more other components that need to be optimized in order to make sure that this is both fault tolerant and the messaging subsystem holds. Thank you very much for your attention, and I'll close out with this shameless plugin for physicians. And in particular, many of you might have heard about this new DOE co-design center called ExcelLearn. So if you're interested in that, please do talk to me. Thank you very much.